Okay, so let's get started. We're going to be taking a look at working with our closed-loop Lambda fuel correction found within our link G5 and G4X programming. Now, this tutorial is going to be doing an overview of how the closed-loop correction actually works and functions. We're not going to get into all of the programming specifics. This is kind of more of the big picture for this feature. This is something that we're going to want to use when we're calibrating and tuning, and then also after we've unplugged our laptop and allow the engine to run on the tune that we've created, allowing the link to make adjustments to our fueling delivery so the actual Lambda and the target Lambda will match each other. So it's something that OEM manufacturers implement on pretty much every single OEM car made with EFI injection. There's going to be a way that the computer can feedback and adjust the base fueling so that everything is correct when you're running your engine, regardless if it's going to be in winter or summer. There's always kind of discrepancies within the fueling delivery, and this allows us to clean that up. We obviously want to make the base fuel table dialed in as best as we can, but there are always going to be discrepancies. And the closed loop allows us to essentially to reduce the error and get our fueling in line to where we want it to be. All right, let's jump in here and take a look at a couple basic parameters, basic things we want to monitor and talk about to understand how the closed loop is going to function. So the very first thing we want to do is have a wideband set up and configured on our link already. Now, we had earlier in the training course a dedicated tutorial talking about, actually two different tutorials, talking about how to set up an analog wideband and a CAN-based wideband. If you're on a G5 system, you have two internal widebands that you might be configuring. So depending on your specific configuration and setup, you'll have to make sure here under our analog inputs, under your Lambda 1, possibly also your Lambda 2, you want to go ahead and configure the details. For this tutorial and for my setup right here, I have an AEM X series wideband wired into an analog voltage input 3. You may be using a CAN Lambda or the internal option. Again, the internals for a G5 only, G4X, actually a G4X Fury would have this internal option. The G4X Extreme and below would have the ability to set up the CAN and the voltage. And then if you're talking about a G5, it's going to have all three options. So right now I've set it up on analog volt 3, pretty straightforward, simple there. And looking at this, if I jump into my fuel page, I can see that the Lambda 1 is coming through here and it is giving me a reading which matches my wideband display gauge in the vehicle. So we're finding that that is going to be an accurate reading right now. When we're taking a look at this, the engine here is running, it's at 900 RPM, approximately 25 kPa, 26 kPa vacuum, 176 degrees coolant temp, 58 degrees air temp, and the measured lambda in the exhaust stream is 0.92. Now, what does this actually mean? Just go over this real briefly here. A lambda sensor is going to measure how much oxygen content is in the exhaust stream. It's not actually measuring how much fuel is being burned. There's definitely a misconception of what that lambda sensor is actually doing. So this is telling me here at a 0.92 lambda mixture that I have a richer mixture or less oxygen in the exhaust stream. If the value went up to a higher number, let's say 1.2, that would be a leaner mixture and I have more oxygen in the exhaust stream that the sensor is measuring. So taking a look at this, we're going to find at idle conditions right now, it's showing 0.92 lambda. In our target lambda table here, we want our engine to run at 1.0 lambda. Now the target air fuel lambda table here has two different parts in our fueling calculations. So in the modeled mode, which I'm operating right now, we have air mass divided by target air fuel equals fuel mass. The target air fuel, target lambda, is part of that fueling calculation. So we want to specify what we want to have the desired target lambda at before we do any actual tuning. And then the other portion is going to be the closed loop control. So this is telling the link if we have a discrepancy here, so the desired target at idle is 1.0, if we're in this case richer or leaner than that target, we can give the link authority to start adjusting our injector pulse width. Again, our pulse width that's being sent to the injector, it can adjust that by a certain percent so that we get our fueling correct, meaning that the actual measure exhaust lambda is going to match the target coming from our table here. So the target air fuel target lambda table has two jobs. One, it's part of the fueling calculation. Part two is going to be part of the closed loop calculations if we turn the closed loop feature on. Now what we're going to find is we have a parameter here called closed loop fuel correction percent. Right now it's sitting at 0. This is the equivalent, if you're used to doing any OEM ECU tuning, of a short-term fuel trim. Right now we're sitting in what's known as open loop. So we don't have the link monitoring what our actual Lambda sensor is reading, comparing it to the target. It's not doing anything. So there's a discrepancy here. We're in idle conditions. We're richer than the target. What we could do is allow our engine to simply run in this open loop condition. We could go in here and highlight the area we're operating at. Right now, that crosshatch is showing us where the engine's actual operating position's at in the table. And I could go in here and let's say shift asterisk, which allows me to go into a mathematical function to reduce or increase my VE values here to increase or decrease the fueling value to the link in its calculations. If I type in here 0.95 and click enter, that'll go ahead and lower the values down here. What that's going to do is lean out my Lambda mixture, my measurement Lambda. It's going to go ahead and run a leaner value. However, that's not that ideal. What we can find is that we can allow the link to take a look at what the measured Lambda is doing, compare it to the target, and then actually mathematically calculate the difference between the two and show what it's making its adjustments by. That way we can use the closed loop fueling correction percent right here and jump into that particular area of the table and make the editing change by that much. So the closed loop correction will guide us in making our fueling changes in our fuel table, essentially telling us how much we need to go and increase or decrease the values by so that the actual and target match each other. The other benefit of running in closed loop is that after you've already calibrated your main table here, you unplug your laptop, you're running in racing conditions, it will constantly monitor what your actual Lambda sensor reading is doing and compare it to the target and make those adjustments on the fly. So the closed loop correction will improve your fueling delivery to your engine, and it's something that you absolutely want to run. So we want to have it for tuning purposes, and we want to have it for long-term engine operation so everything is dialed in properly. Okay.
Thanks for checking out our teaser clip. If you want to see the rest of this video and more than 500 hours of current EFI training we have to offer, make sure you click right here. If you want to go and check out more teaser clips from this training course, click here, and you don't want to miss any of the videos we're going to be releasing on this channel, so make sure you subscribe and click here. Thanks for watching, and I'll see you guys later.